Well, thank you very much for coming. I'm really excited today to have Chris Grenade here to talk to us about his research. Chris Grenade is somebody who I've known for quite a few years. His work largely has looks at the question of what information can we extract from quantum systems. He did his PhD under David Corey at the University of Waterloo, where he did a number of things. It largely pioneered the use of approximate Bayesian inference in device characterization and also data analysis. He's worked on a number of experimental platforms ranging from nitrogen vacancy centers to neutron interferometry, and also has a wide range of experience in software development, where he's developed a Q-infer package, which I think we're going to be hearing about today, for statistical inference, as well as a number of other neat and amazing skills. So with that, I'd like to have Chris begin. Thanks.
Thank you very much, and it's a pleasure and an honor to be here. Today I'd like to talk about a lot of that work, screen timeouts, with the good, the bad, and the practical. So getting right into it, what do I mean by this, right? The good and also kind of the bad is that it's really challenging to build a quantum computer. It's a hard thing, and we run into challenges in a wide variety of different fields, everything from condensed matter and mathematics, computer science, through to electrical engineering, programming, right? So, there's a lot of interesting problems here to solve, and there's a lot of interesting problems we have to solve. So in doing so, we want things to be practical. We want to build things that work. So what do we mean by that? Well, part of what I'll get at in this is how can we build up methods that are well understood, right? That build on solid statistical and mathematical principles so that we can generalize them appropriately, so that we can understand the limitations, so we can understand how to move forward with them. We want things that are generic so that we can generalize them, we can modify them. It's no good having a solution that only works for one experimental modality if we then realize that modality isn't what we want to be doing. It doesn't work to say have something that breaks the moment we introduce a different model of op-amp into our system, right? We need to actually have something that's generic enough to be a platform to go forward with building a quantum computer. We need something that's efficient, right? If we're trying to build something that's better than a classical computer, we can't be introducing bottlenecks here, right? This is not the stage that we want to be. We need things to be efficient, and one way to do so is to really leverage modern hardware like FPGAs that get down to the experimental control. So largely I'll be talking about this practicality from the standpoint of characterization, because this is something that comes up in a lot of different stages of building a quantum computer. Everything from calibrating, looking at Rabi and Ramsey interferometry, where you're trying to learn static fields or the power of a pulse, to learning crosstalk, what qubits are affected by that pulse. Once you have something, what kind of a state or a channel is affected by your control? This is a powerful way to diagnose and debug and give you the feedback you need to go forward. Once you have something, how do you verify that it works? How do you convince somebody else in your own group or in the public that what you've done works? And there's tools like randomized benchmarking and quantum Hamiltonian learning to do this. And characterization even comes up within algorithms themselves that we're trying to build, if we look at something like phase estimation. And this is where I really want to treat it as a jumping point and look at iterative phase estimation, because this is a really neat example of where a lot of this comes up. Right, so we'll start by preparing a state that is known to be an eigenstate of some unitary, but where we don't know what the phase associated with that state is, what the eigenvalue for that is, and where we want to learn what that phase is. So one way we can do so is we prepare a control register in some fixed state, act a Hadamard, do a rotation, and then use that to apply that unitary and measure our control register. This setup has the very nice advantage that our state, that is the resource state, the eigenstate whose phase we're trying to characterize, we get to reuse, right? We know it's an eigenstate, so it's in the same state at the end, and so we can do this iteratively, and then the cost comes in this controlled unitary. And if I look at the probability of getting a 1 there, a click there, it goes as a cosine in the difference between the phase that I'm trying to learn and some control that I get to apply. In this model, it seems somewhat simple, but it has a lot of rich applications. Everything from looking at interferometry and metrology, so building quantum sensors and things like that, to calibrating away errors in gates and trying to make more robust gates by learning what over-rotations there are in the system, to quantum chemistry and simulation, where we'll get into this being a big part of the cost estimates in a moment. But what's really critical going forward about this is that phase estimation is actually two different problems coupled together. It's a statistical inference problem. How do I assign an estimate given some data? And it's an experiment design question. How do I pick the next end that I should use to gather data? Solving these looks like a functional constraint in that the costs, for instance, in the algorithmic applications of iterative phase estimation, wind up occurring at outer loops of very important things like quantum chemistry, such that an improvement to phase estimation there can be a make or break for the entire application. So we really have a strong functional requirement on what solutions we develop here. But even more than that, it's also a design cycle that helps us get to that kind of a functional point in the first place. And that an accurate characterization feeds back in and tells us how we should change our device, how we should change our control on the device to do better at the next iteration and reach the kinds of noise levels we need. So there's a number of examples of this out there, everything from using robust variants to do gate calibration, and then more generally looking at design cycles as characterization. We can do things like learn error models from the syndromes we see in error correction codes, use that on logical qubits to then learn how good our our error correcting codes and our decoding algorithms are in practice. And use that to select new codes and new decoders appropriate to the noise models we actually have in practice. So going back to the example of phase estimation then, our solutions really should carry this practicality forward, and it should respect the fact that there are these two different problems. Right? So how do we solve the first one? We've introduced a new tool, rejection filtering, that's FPGA compatible for doing approximate Bayesian inference close to experimental hardware in a way that addresses the statistical inference half of phase estimation. And then we pick experiment designs using heuristics. So we'll choose our M's based on the current variance in our posterior over that phase we're trying to learn. And that gives us something nearly optimal. And together, the two of these give us a very powerful tool moving forward and something that dramatically outperforms existing techniques. So I'll get into what this quality parameter M is in a little bit, but depending on our quality parameter, we can do dramatically better than existing techniques like Kitaev in terms of the number of times we have to apply that controlled unitary. And just to back that up a little bit, it's nearly optimal in the sense that we get 3.3 over epsilon scaling compared to pi is ideal. So we're paying only a very small constant for something that can be embedded close to hardware and is efficient to approximate. And that allows us to relax a lot of design constraints, right? If we're paying less to do these measurements, then that means that we have a little bit more slack on the other kinds of things which are quite difficult as well, so qubit counts and error budgets, what have you. And critical to this, again, is that we've brought things down to the experimental hardware, so it gives us a lot of flexibility in that sense.
The question is it known what the optimal
is? From Heisenberg scaling. So if you run through the Kramer-Rao bound, you get pi over epsilon is the least M required, least M that it required to attain an uncertainty of epsilon.
Is it independent of the operator U and the eigenstate?
Well, so it's a property of this circuit here, right? Because as soon as I get it down to this description in terms of a cosine, there are other bounds that give you order 1 on epsilon for say parallel copies of and what have you. And I don't remember the constants. They may also be pi. I don't. Okay. What I do remember is that specifically for this, though, it is literally pi to all constants. And In this case, there's a lot of quantum arguments people give, but I find the simplest way to see that is to run through Fisher information and Kramer-Rao bound, and that we've reduced it down to, like, once we've said what circuit we're using, it's now a classical statistical problem to figure out the bounds on cost.
So for this choice of M, can the classical inference problem still be solved efficiently?
Yes, that's what this, yeah, exactly. So importantly, so the next thing I want to mention about this phase estimation is that we encounter very similar examples elsewhere in characterization. So I mentioned Ramsey estimation, very similar to Rabi estimation as well. But we can start by saying we have a Hamiltonian that is proportional to sigma z with some unknown frequency. And then kind of the traditional way people often go about solving this is they'll prepare a plus state, so something orthogonal, something with support on both 0 and 1, evolve under the unknown Hamiltonian for some amount of time t, and measure a click that goes with that same probability, right? So the same cosine squared comes up here. And then they'll repeat this for many shots to estimate the probability of that click, and then they'll do that at many different times to estimate a signal, and you'll get something that looks a bit like this, right? So as I start with 1 shot per time, 10 shots per time, and I go forward, you can see more and more clearly out of the data what that signal looks like. You can then back it out using a Fourier transform. So in this case, I use 70.3 megahertz. So, this is telling us the peak, okay, that's near 70.3 megahertz. But we don't have to do it that way. We can do a lot better, right? So if we take a Bayesian approach, the same sorts of tools that, we develop over on the phase estimation side and apply them here, we're using the one-shot data to get very accurate estimates of a physical quantity in the system we care about. And having said that, we can then incorporate more models for more kinds of physical effects as well. So for instance, that op-amp comment at the beginning, that's actually a thing that we run into. If there's some physical component that doesn't act in the ideal way we'd like it to, we can include a model of that and build that into our estimation procedure. And that's very useful, for instance, looking at nitrogen vacancy centers with learning the Hamiltonians of those with quantum resources, or using a nitrogen vacancy center to measure vector fields, even when your apparatus is drifting because of thermal expansion in different parts of your system, right? So and this is very difficult to do if you don't start with something that is general enough to build on. And taking it all together, it suggests a really good way forward to building the kinds of tools we need for quantum information processing. In that both of the problems we've looked at, phase estimation and Hamiltonian learning, are special cases of a more general problem called parameter estimation. And if we use the best tools we can there, we get practical solutions that work for us and relax design constraints elsewhere. So parameter estimation just says, given some data, and a model that I would like to learn, what should I estimate the parameters of that model to be? And I can express a lot of different things in this language. I can express Rabi or Ramsey estimation, as we saw. I can express crosstalk, what Hamiltonian actually gets applied when I turn on this pulse. Randomized benchmarking, generalizations of randomized benchmarking that are very difficult to analyze elsewise become quite straightforward in the parameter estimation view. State and process demography, or even learning things like what noise sources you have in the environment that might be affecting your controls. So thinking about spectral density and noise spectroscopy is very straightforward to do in this framework. So just to run through this, a couple of examples of how to take a problem and write it in that language. If we consider an unknown state, rho, that we would like to learn, and some measurement that we've performed with effects Ej, then Born's rule tells us that the probability of seeing a particular outcome described by Ej is just an inner product with the state. So the trace of Ej against the state that we're trying to learn. But we're trying to learn that. So we use Bayes' rule to invert and write that back out in terms of the state, what the probability of a state is given some evidence that we've seen, given a measurement outcome. And we do that by reweighting using Born's rule. and then dividing by a normalization factor. In practice, it's common to write this out in some parameterization in terms of some basis, as we'll see a little bit more later, such that I can think of my state as actually being some real vector in that basis. A little bit more detailed, we can also look at randomized benchmarking. This is really neat because it's a widely used protocol already to do characterization and to report fidelities and to tell how well your gates are doing. And essentially what it does is it uses random sequence of Clifford gates to try and randomize errors and make them more tractable to simulate and give you a much simpler model. And it's turned out to be a very rich platform as well to build additional tools off of. So from the basic RB theory, we get everything from interleaved, where you can say, I want the fidelity of that gate, to looking at unitarity, where you ask about coherence instead, dihedral, where you don't have to restrict yourself to Clifford sequences, or logical, where you use the structure of error correcting codes to do that randomization for you. And what's critical to all of these is that we can take quantities of interest like the channel fidelity and write them as an average over the discrete Clifford group. So I can say a twirl, so that if I have a channel lambda, the twirl of that, W of lambda, is an expectation value over that finite group. And what I get out is that it either acts as identity on a state or maximally depolarizes it. And the ratio between those two is exactly related to the fidelity of the channel of interest. So if I know this simple channel, then I know that the P describing that simple channel, I know the fidelity that we cared about at the start. So let's take a gate, UI, and say we have a noisy version of it. So it's actually the ideal UI followed by some noise channel. Then if I pick a random sequence of gates, I can start with my state, my initial state, apply random sequences, I get a copy of the noise after each, and then I do some odd-looking measurement here, but by a clever change of variables, we can get it down to that it's actually just the measurement I had access to all along, and then gives me each copy of the noise channel seeing the same gate and its inverse on either side. So that is exactly what happens in the twirl, even though I didn't have perfect gates to do that twirling. And so now if I average over that, I get a simple exponential decay that goes as the probability of getting the identity channel part of each of these twirled things, and then some constants A and B that describe the errors in state preparation and measurement. And so now I've reduced everything I want to know down to learning that P and scalar multiplication and addition rather than trying to think about the open quantum system simulation of that circuit, regardless of the dimension. So if we interpret that as a parameter estimation problem, then it asks what the probability of that final measurement being observed is conditioned on that simple model, P, A, and B, and the fact that I chose a sequence of length m. And so it tells me that given a hypothesis, that the probability is just that same simple exponential we saw earlier. And again, doing the Bayesian inverse, we get back to a probability over that fidelity and those spam errors conditioned on some evidence. And it works by reweighting each hypothesis by how well that hypothesis explained the data that we saw. Like phase estimation, this kind of a description makes it really straightforward now to see that it's two different problems that are coupled. Given a set of observations, what should I use to estimate P, right? But then the other is how long should I choose the next sequence to be, right? And that we can ask that now in terms of that Bayesian inverse, in terms of that parameter estimation language, and it provides us a common framework for answering both of those problems. From an experimental perspective, this is maybe not what you want to do. You want to, get things done. You want to, go build the next experiment. So we also want this to stay out of the way and be a tool, a useful tool going forward. So we use principled statistics to reduce data collection, to provide the accurate estimates, and to do so in a way that makes it easier to communicate with others internally or with the public as necessary. So to address that, we'll build principled statistical algorithms and implementations of those algorithms, and then we'll use those to build experimental design heuristics that let us get things done. So for the first part of that, algorithms. The real workhorse of this approach is particle filtering, which takes and represents our beliefs about a model by a set of hypotheses. So I'll write those down as those vectors x, and associates a weight to each of those hypotheses, initially uniform. And then if I want to estimate x at any time, I just take a weighted sum of each of those individual hypotheses times the weight associated. And then the update does exactly as we saw earlier in both the phase estimation and randomized benchmarking and the tomography cases, where we multiply the weight by how well that the hypothesis with that weight explain the data that we've seen. And then we renormalize to make all the weights sum to 1. There's a little bit of a problem we run into when we do this, though. And that is we very quickly wind up in a situation like on the left, where this is 1,200 particles, but if you look at it, most of them aren't doing much. You only see a few here in the middle that are actually carrying the information we want out of this approximation. That there's a whole bunch of particles out here that are difficult to even see because they're not participating in the approximation. On the other hand, with much fewer particles, like the 400 over here, that's the same distribution. And you can see the structure a lot more clearly out of it because we're using the density of locations rather than the weights to represent. So every one of those particles is really doing something with the approximation. So we can recover our numerical stability and get back to something that looked like the right-hand side of that by contracting our hypotheses toward the current center of mass of our approximation, and then convolving with a Gaussian to add back in the noise that we removed when we did that contraction. And that preserves both the estimates and our uncertainty in those estimates, and it puts the weights back to uniform such that each of those particles is really doing something. So here for a simple problem, which is 2 cosines instead of 1, which actually turns out to be useful. You can watch as the particle filter approximation trades off between these two dynamics of updating the weights using Bayes' rule and then using this resampling technique to contract everything toward the current center of mass and add back in the amount of noise that was removed. And in a fairly small number of steps, it winds up getting to a good approximation of that true state that we use to generate the data behind this. It's a statistically principled algorithm in that it's providing us a rigorous approximation of Bayesian inference. So, this gives us all of the statistical principles underlying Bayesian inference as well, including an explicit dependence on the prior. So this is often kind of sold as a problem, but I'd like to turn that around and say, look, you disagreed with me on my assumptions, and you can tell because I wrote them down right here. You can point at them and change them, right? So a large part of what this does for you is it gives you the statistical principles that make your assumptions clear. It makes the effect of those assumptions clear, and in a way that's very general and extensible. We can build a lot on this. All I had to say about the problem of interest when motivating particle filtering here is you update the weights by multiplying by some function, right? Well, what's that function? So that gives us something very general in that we can plug that function in a very black box way. And in doing so, we still get out the rich error reporting and heralding of failures of particle filtering, where if, for instance, very few of those particles are contributing by the end, it tells us something probably went wrong in our numerical approximation, or because we were using the wrong model and we need to look at a different model. So it's a very powerful diagnostic tool there as well. And our implementation tries to build on this by supporting common applications in quantum information, including Hamiltonian learning and phase estimation, as we saw, randomized benchmarking, and tomography. In doing so, we wrote our software for people, not for computers. We wrote it to be accessible to the people who are trying to use this, meet them in the middle on using common languages as used in experimental practice, from Python to Julia and MATLAB, open source so new teams can get up and running with it quickly. It's portable. We didn't want to make assumptions about what operating system a theorist might be running their simulations on, and we didn't want to make assumptions about what hardware drivers might constrain an experimental application, so it runs on all major operating systems out of the box. We've provided about 100 pages of documentation, examples, and guides, and API docs, all to support that. And we've tried with the API design to make it expressive of the underlying scientific and mathematical concepts, such that it shouldn't feel like writing something against an API. It should feel like describing your problem. And finally, it's extensible, right? We pretty much assume that people are going to want to write their own models for the peculiarities of their experiment, for the peculiarities of their applications. So we've really tried to support that by making a very flexible framework to do so. So here's the installation instructions for our package. It's on pip, so any standard Python install, you can just do that. For Julia, we need a little bit more interoperability support, so 2 lines. And to use it, all right, you can make the data however you like. Here is actually how I simulated the thing on the earlier slides. But then the interesting part is we process it by stacking it up and feeding it to one of the simple models that's already built in. And that's that. You get out the estimated mean and covariance just from that. And it looks very similar in other languages, like MATLAB or Julia. And if I apply this, we also have cases like randomized benchmarking, where here I can say, feed in a fairly small amount of data and get out the posterior distribution over fidelity quite efficiently from that, and characterize my uncertainty in doing so, and do so in a way that is statistically principled and provides an experimental benefit with that. A little bit more complicated example comes up in tomography, where here you have to say a little bit more about what you mean. So we'll start off by defining a basis. Pauli bases are built in, so you can just do that and say a 1-qubit Pauli basis. You have to then specify your prior. Here I've chosen the Ginnebrey prior, so that's a very general distribution that includes both Haar and Hilbert-Schmidt uniform as special cases. I've chosen the read-it version, so that is one that has no complex numbers, because that makes it easier to plot. But if you have a y-axis in your system, because presumably that's actually, then Ginnebrey distribution works as well off of the same basis. I can then use that to define a model, so that's that likelihood function that describes the probability of getting a particular outcome out of. I'll choose a true state, initialize my updater, so that is the thing which implements this particle filter, for that model and for that prior, with a modest number of about 8,000 particles for this. And I'll get more to this in a moment, but I'll choose experiments in that by randomly picking a Pauli operator and performing that as a measurement. I can then loop over the individual experiments, asking that heuristic which experiment to do next, simulating the outcome of that experiment, then feeding it back to update the posterior distribution, and to get a description of my uncertainty in what the state is. So this is actually what the code on the previous slide actually generates. Is you get an estimate of the state, you get that's the true state we use to generate it, and you can see each of those particles telling you about different hypothesis and its relative plausibility, and we can put a region around those hypotheses to get a very principled tool for saying, here's where we think the state is. And this with only the 500 single-shot measurements. That's backed by Q-tip. So if you want to then hook into other things using Q-tip, like looking at Staaten norms or diamond norms or things like that, you can get out all of the different parameterized representations and Q-tip Q-obs from the Q-infer representation that we use internally. The last feature I'll mention of Q-infer before moving on to bigger and better things is we can also support time-dependent estimation with this as well. So now if I say, after some time tk, I want to know where my model will be at tk plus 1, I can put a diffusive rule on that and sample, move my hypotheses according to a Wiener process. And doing so allows me to track time-dependent problems. So for instance, here we set a slowly varying static field. So that is, it looks static for any one experiment, but if you look over the course of microseconds, the Rabi oscillations in this problem are changing. and on the order of hundreds of megahertz. And we can track that quite well. There's always a little bit of lag because we're trying to track a process, and our data lags behind that a little bit. But this gives you a big advantage over trying to start from scratch every time, and that if we're sitting here, we know something about the estimation problem immediately before it. And that's very natural to include in this sort of a particle filtering framework. The other thing I want to mention, though, about particle filtering, aside from just how to implement it, is that it's also a very good intellectual basis for going forward and coming up with new algorithms entirely. So rejection filtering, if we take that resampling procedure I mentioned earlier with contracting things toward the mean and adding back in noise, I only need to keep one particle in memory at a time if I do that contraction all the way to the mean and add all that noise back in. Right? If I think of things as being in the Gaussian limit where that contraction and resampling process entirely describes my posterior. And if I only have to remember one particle in memory at a time, that gives me something that's very easy to implement in practice because of that low memory. And in particular, it's then ideal for embedded characterization, in that I'm asking very little of the embedding device. And the algorithm you get out of it is simple enough to fit on a slide. So here I'll say, given a prior mean and a prior covariance and a number of samples that I want to accept, so that's that quality parameter m, for each data min experiment, I start by initializing registers for how many particles I've accepted and the sum of the squares that I've seen so far. Until I've accepted enough particles, I can sample a new one, accept it with a probability given by that model, that same likelihood function that is what describes our problem of interest. And if we accept it, update the number of particles, the sum of them, and the sum of squares, and use that to estimate the moments and go back and start the whole thing over again for the next datum.
That's nice. What's the expected number of runs you need to do in order to produce a sample? Scaled with 1 over the probability, right?
Well, that's why this is iterative, is because then we're only looking at the probability for a single outcome. Right. So I mean, if you have an outcome that's exceedingly rare, this will collapse. And it will collapse for the same reason that particle filtering collapses. And in general, it's very hard to reason with that. And there are things you can do. You can do things like use model selection to tell if you're in that case and reset to a good prior change models. So it's not like a fatal flaw if that happens, but that is where these kinds of things force you to look at other techniques on top of this. So does that answer the question?
Yeah, sure. It's the same as in rejection sampling, right? The same idea.
Well, we use rejection sampling here, but the critical difference from just straight rejection sampling is that we're using this Gaussian approximation to reset that rejection sample every iteration, instead of trying to reset rejection sample on the entire experimental history. So that is that under very common applications, such as phase estimation or things like that, the expected probability of accepting a sample is constant. And so we don't run into that exponential decay that I think is that? Yeah, so we don't run into that here because of that. What we need is that the single shot probability remains far enough away from 0 that it's reasonable. And if you have, like I said, there are other techniques I omitted from the description on the slide for simplicity, but if you know that none of the outcomes are more probable than k, you can renormalize before doing your rejection sample, things like that. So that there's a number of techniques you can deal with that case when it happens. But as stated in the simplest form, that is the edge where you have to start looking at other things as well. Building on this idea also lets us then build other algorithms entirely, including quantum algorithms. So say that now instead of doing a classical Bayes update, I want to do a quantum Bayes update. And I have some register representing my prior, and I'd like to map it into a register representing my posterior. Here using amplitudes instead of probabilities. This is not a linear update. So it can't be, I need something else. And the HHL algorithm allows us to use post-selection on ancilla to do so. And rejection filtering allows us to recover for exactly the reasons that we just discussed here, right? So it gives us a quantum algorithm for performing Bayesian inference using this kind of a particle filtering idea to build our way up to it. If we go back to the classical side, we can use machine learning techniques to reason about the performance of our particle filters in a very structured way. And that gives us something that's critical for dealing with multimodal or degenerate problems where the resampling procedure I mentioned earlier starts to fail. And the key idea that we'll use in doing this is that instead of trying to resample the entire posterior, we'll split our particle filter up into different modes and resample each one locally so that we don't run into these kinds of edge cases and then learn how that modal structure looks for our actual posterior. And we'll use a graphical notation to do so, where we'll take all of the particle filters we've seen so far and call them boxes. A question of whether one or another particle filter is more a better explanation of the data we'll represent with a circle. And if we have a mixture, so that is a question of is it this mode or this mode in the posterior, we'll use a triangle for that. And so then this sort of a thing says I have a particle filter. This says I have either two modes in my posterior, two peaks, two plausible explanations of the data, or I have three. And I'm not sure which, right? So you can split and say, I don't know whether I should do 2 or 3 modes in the posterior, and then use the data to resolve that question up at the top. And if we let this run on a problem here, which has 4 modes in the posterior, so there's about here, 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 and here, 4 true assignments to the actual model of interest that are equally equally supported by the data that we observe, right? Our experiments cannot distinguish between those 4 possibilities. And we've told our algorithm there are either 1 or 2 clusters in the posterior. So we're being a little unfair to ourselves in this. And it's trying very hard to make it be 1 or 2 clusters. And you can see it effectively trying to make that a cluster, splitting them up recursively to find that structure. And I personally find this, I can watch this way too long, but if you run this long enough, you can watch it collapse down to something like this that really does describe it found those 4 modes in the posterior, even with that 1 or 2 mode restriction. And it did so by making mixtures over trees that are minimal for that. And so the weights of the shades indicate how well that path through the tree is supported by the data. And we see that this model selection, for instance, here is primarily supported by a mixture over a single mode. So this circle has 1 mode. This circle has 1 mode. This circle has 1 mode, and so forth, right? This is really telling us there are probably 4 modes in the posterior, and you can do region estimation on top of all of that, and it gives you a lot of insight into the structure of this problem, where you can go, maybe I should come up with an experiment that lets me discriminate between these 4, else I'm never going to get anywhere. And that's an insight we intentionally did not build into the algorithm. We're trying to use this as a tool to find it, and it did for us. So in the last few minutes, I'd like to talk about the other half of this. Now that we have a platform for looking at these kinds of statistical problems, how do we use that to build experiment design in a way that's also efficient, also practical, also gives us a tool going forward? So when we do so, something that's really critical to remember is that even in the worst case, data is still data. So it's a little bit different from looking at the statistical inference side, that we have a little bit more freedom in picking experiments, that we don't have to guarantee that it works in every single instance. We can use, and that gives us more room to use heuristics. And in doing so, we note that in many cases, we're rewarded for picking experiments randomly because we need to decorrelate different parameters, and it's very difficult to do so until you have enough knowledge about those parameters anyway. So for instance, in the tomography case, randomly picking different axes allows me to decorrelate errors between those 3. And the fact that I need something simple enough to, again, embed in hardware, these all push us towards thinking of things heuristically, where I'm not trying to solve the exact optimal experiment choice, but I want to pick something that works in practice. So one very nice example of this is self-guided demography. So it's a recent proposal by Ferry. My apologies, the citation is not showing up properly. That expresses tomography as an optimization problem. All right, so instead of now asking what the state is, I ask what measurement do I do that gives me the best overlap with an unknown true state. And then this looks like an objective function that I can evaluate by measuring, just counting a number of clicks if I do that measurement and I have that state as my true state. And this objective function is maximized if the measurement I do is the dual of the state of interest. So that is, it's the state which has the best overlap with the unknown state is the unknown state. So if I throw this at a stochastic optimizer, I can find an estimate of the state that way. But I build in a lot of assumptions here that I don't really like that it's pure and things like that. So on the other hand, I can also treat this as a heuristic, that even if the stochastic optimizer doesn't work in the sense that it doesn't give me the statistically principled estimate I want out, it still collects useful data. It still says, evaluate that objective function here. And that looks like a description of a measurement. And if I do that, and I keep all the data this stochastic optimizer collected in order to solve this problem, and then I just post-process it with Bayesian inference, I get a principled estimate out that does what I want, even when the assumptions going into the stochastic optimizer are explicitly and maximally broken. So here I've taken a mixed state on qtrits and told it, go find the closest pure state on qtrits. And the self-guided approach is throwing its hands up and saying, I don't know, because we've been really unfair to it. We've maximally broken its assumptions. But if I take that same data and analyze it using Bayesian inference, so that is the practical adaptive quantum tomography scheme that we proposed, we still do quite well. And we're beating more traditional methods like least squares fitting when we have fairly small amounts of data, which is where we'd like to be sitting for a lot of this, right? You take enough data, the same sort of post-processing works fairly well for more traditional methods because you've gotten away from boundaries, but we still have the advantage of robust error bars, incredible intervals, and all the other sorts of principled things that we built up. The same kinds of ideas of using heuristics work very well in other examples as well. So if we're trying to learn a Hamiltonian by interacting a system with that Hamiltonian with a simulator that we have access to and we know is good, excuse me, we can get something like this where we now say we need to pick what Hamiltonian we evolve backward by, what we try to invert by to learn here, and how long to evolve for. And one very important thing about this experiment design is that we can do the particle updates for this algorithm. We can by simulating only on our trusted good device. Right? The swap gate doesn't do anything in principle. It's rather how we interact the system we'd like to characterize with a system of interest, with a resource that we have. So that leaves open the question of how to pick the inversion Hamiltonian. And one way, so we can go back to the particle guess heuristic and do it that way. We'll pick two hypotheses out of our current posterior, and we'll use one of them to do the evolution, and we'll pick a time that goes as 1 on the difference between the two. And that gives us the advantage that the norm of the inversion Hamiltonian times the time we apply for is approximately constant, such that if I look here, the low-Schmidt echo at my data, at my measurement is approximately constant in width. So that is that these this measurement doesn't run into the problem that we talked about earlier, where all of the probabilities go to 0 or all of them are the same, right? I mean, that I'm getting a good discrimination between the different hypotheses in my particle filtering approximation. And if I apply this to learning in qubit Ising models, so here we took a complete graph on 3, 5, 7, and 9 qubits and applied this heuristic and particle filtering with a simulated quantum resource, we can learn quite well and get quadratic losses, so that's multi-parameter generalizations of mean squared error, that decay in the same kinds of exponential ways that we like to see out of these problems, the same way we saw out of phase estimation and frequency learning. And this is very useful, again, if we now use that and we build up that trusted quantum simulator using copies of an unknown state that we'd like to learn, and interact it with our quantum simulator. And this gives us another approach to doing tomography that we call blameless tomography. And the reason for that is that it breaks what has been coined in the literature as the blame gauge, where it says, I don't know the errors in my preparation, my errors in my measurement separately. And by introducing this partial swap protocol based on the Kimmel et al. Or the LMR algorithm, we get a knob time that lets us make the errors in state preparation appear differently from errors in measurement, and reduce back to the same kind of statistical inference problem we saw out of quantum Hamiltonian learning, and that now we're trying to learn the Hamiltonian implemented by the pairing multiple copies of the state and partially swapping them on, so e to the I rho t. And using the same sorts of heuristics, this purple line shows us the best we could possibly get out of Kramer-Rao-bound style arguments. And what we actually get is parallel to that, right? We're setting some constant away from that because we have to pay some constant overheads to make to implement the LMR algorithm at all. But we're parallel to the best that we can do. So we're getting the same kinds of scalings that we'd like out of tomography, and with this additional benefit now that we can make the measurement and preparation of errors appear differently. We can go even further with this and include physical insight out of condensed matter, like Lieb-Robinson bounds, and extend this benefit to looking at systems as large as 50 qubits, where here I might start with some observable on an untrusted device, evolve it forward, and then use that evolution to try and reverse that light cone away. And maybe there's some little gap here where, that because I haven't picked the exact same inversion as the true state, right? But then I can bound how much error I incur with that by using Lieb-Robinson bounds. And what's really cool about that, and what I really love about that, is that the Lieb-Robinson velocity describing this evolution forward then backward on the trusted device, the velocity slows down the better we know the evolution on the untrusted device, such that we can scale in the same kind of way that these heuristics give us a useful thing to get the same kind of exponential decays in error that we saw in other problems. Even looking at 50-qubit Ising models with an 8-qubit simulator and probing 4-qubit observables on it. So we really get something that can build up to some of the largest challenges we have at the moment in these sorts of systems. In all of the cases so far that I've talked about with heuristics, though, we've had some insight that's let us say, what is the most appropriate heuristic? What constants should we choose? If we don't have that insight, we can still do something now where we go a step up and we talk about hyperheuristics. That is a family of heuristics with some vector we'd like to learn that is the best heuristic to use in that scenario. And we'll pick the best heuristic to be the one that minimizes the average error, that minimizes the risk. And QInfer lets us do this. We can feed in a model into our performance tester, and it will run that repeatedly, parallelizing if you tell it to, for a given prior and a given heuristic, and tell you what the risk is, how long it took to simulate diagnostic information for each different trial. And if we use that together with some novel extensions to particle swarm optimization, with very minimal insight at the start, we can get nearly as good as the best heuristics out of that. So, we're not quite beating like existing PSO on this, but we've done so with significantly less insight in a way that we didn't have to build things into the problem to start with. So together, these statistical tools and experimental design heuristics really give us a powerful approach forward to relaxing design constraints on some of the hardest problems we have to face in building quantum information processors. And with that, I'd like to thank you for your time and answer any questions you might have.
Great. Well, thank you very much, Chris. Questions?
So I have one question. Okay, so can you maybe clarify once more where is this kind of the rigorous and non-rigorous parts in using these methods, right? Because, I mean, as far as I understand, the particle filtering is a kind of not. Is it? I mean, I guess it's a question, right? Is the particle filtering approach is actually a rigorous method, or is it a heuristic?
It is a rigorous method. It's still a randomized algorithm, and as such, there are finite probabilities of failure. But there's a very nice paper by Peskos that talks about how to bound those. And one of the things I really like is that that Peskos gets into there is that it's also heralded, right? So it's randomized as an approximation, but you do have insight as to when that approximation has failed and can try again, or can, up different quality parameters to make it succeed. But so from that standpoint, it is a rigorous approximation to the exact Bayesian inference problem. And so that's totally rigorous. The rest of it is also rigorous in the sense that the experiment design heuristics, once you pick an experiment, then you have a rigorous answer to what you know having done that experiment. So that is, you don't sacrifice any principles or rigor in choosing experiments heuristically. And that's part of why that's a really good target for using heuristics, is you still get the rigorous answer out at the end.
Okay, so the heuristics only comes in experiment design.
Exactly.
Can you comment on the issue of error underreporting? Like randomized benchmarking can lead to underreporting of errors.
That's a very good question.
Can you, do your methods help with that somehow?
They do. It doesn't entirely solve the problem. I don't want to overclaim. And part of that is because there's a few subtleties in the randomized benchmarking model that can occur even at the experiment design stage. So if I look back at, earlier than I thought. So if I look back at this, the key thing here is this expectation value, right? Where I've said every time I do a measurement, the fact that I'm taking an expectation value here means that I need the mean of this measurement to be a sufficient statistic. And that's true only for the binomial distribution. So that immediately implies you have to take one shot per sequence in order to meet this sort of statistical principle. And if you're taking more, then you could not be including the variance of that properly in ways that could lead to underreporting. It could also lead to overreporting of errors. It's difficult, like we don't have a good framework to analyze when you take many shots per sequence. And I think that's a good open problem. But this is the first effort that lets you deal with that in a rigorous way. The other problem that you run into, though, is there's some hard boundaries to this problem, right? So if you have a fidelity that's very, very close to 1, then you get into the same kinds of boundary arguments you get out of tomography. And that's where the heralded properties of the particle filter approximation didn't work very well. But kind of the simplest thing you can do is put a prior that says, I have a fidelity that's at least something. So like in practice, if I want to get 0.995% fidelity out, I have trouble if I don't set the prior to be better than like 80%. But you're not going to say, somehow that seems like a fairly modest assumption to say my fidelity could be as bad as 80%, right? You have a gate at all that's you want to characterize, so even saying that. But heralded, model selection, things like that let you deal with these kinds of issues.
All right, well, I have a question then.
Yeah.
So from your perspective, what are the most pressing parameter estimation problems that we have to deal with at this phase of quantum computing?
So that's a very good question, and I think that one of them is one that I would like to have put on here, but I didn't, because it's something that comes out of communicating, a more robust communication than I think we currently have as a community. But and that is being able to include device parameters explicitly into the kinds of characterization procedures we're already doing, such that we can talk about things like crosstalk models more accurately, talk about efficiency of amplifiers better, that we really that if I want to be able to do good control and treat this as a design cycle, I need to be building more, I need to be hyperparameterizing my models based on descriptions of the actual experimental hardware in a more accurate way. And even using tools like model selection to answer questions about what experimental hardware is doing by taking different alternatives there.
Then let me pose a follow-up question. So you promised us the good, the bad, and the practical. I'm kind of curious, can you give a characterization of, amongst the methods that are being used right now, what features are good, what features are bad, and what features are important for practical?
So I mean, the thing that I feel like is a really good resource to build practical tools is to fall back on the statistical principles. To say, write down your problem as concretely as you can and work out what the statistical inference is from there. And that gives you the ways that we've seen of relaxing design cycles, of relaxing design constraints, enabling more heuristic methods to be used on top of that. And so from that perspective, I'd say the bad is when we aren't careful enough about what the underlying statistics are, when we aren't careful enough about describing the problem that we're trying to solve. I mean, often the description is really the majority of the work. Once you have it described, the algorithm becomes obvious in this sort of a language and sort of terms of this framework, and it might take some effort to implement it, but you at least know what you're trying to implement. So the bad is that sort of vagueness about the problems we're trying to, right? If I'd emphasize anything out of this, the path to practicality for quantum information is being specific about what the problems we're trying to solve are.
Any further questions? All right. Well, if not, let's thank our speaker one more time.